Hi there, this is Matt Heffernan. Welcome back to my channel. This is the second episode of my tutorial series on Z80 assembly language development, targeting the Sinclair ZX Spectrum to learn how to program a simple system starting at the very lowest level. If you haven't seen the first episode, I strongly encourage you to go back to my channel. And don't forget to subscribe and click the bell to be notified when the next episode comes out, and start this playlist from the beginning. This series assumes that you already have some familiarity with programming in a high-level language, and some rudimentary understanding of things like hexadecimal numbers and Boolean logic. If you don't, I would recommend checking out the many videos and websites out there that can get you started on those topics, and I have some linked to my GitHub repo page that's linked in the description below. In the first episode, we went over some of the basics of what assembly language is, and what that means for the Z80 processor and its use with the Spectrum. In this episode, we are going to learn about all of the different addressing modes provided by the Z80, and show how all of them work in an example program for the Spectrum. But first, we need to define what we mean by addressing mode. When we talk about addressing in a computer, we usually mean memory, and the Z80 has 16-bit addressing. This means that there is a 64 kilobyte memory space. So if a Z80-based system were to have more than 64K, it would require banking, which means that addresses could refer to different parts of memory based on the current bank selection. This is the case with the 128K spectrum, but the 48K spectrum does not require banking. Each of those 65,536 addresses refers to a singular byte in memory. The first 16K of memory is read-only, which is why we call it the ROM, for read-only memory. The remaining 48K is random access memory, or RAM for short. This memory we can read or write to, but some parts of it have specific purposes, like the screen memory, which will affect the display when we write to it. But how we read, write, or even execute code within this memory space is entirely controlled through the use of different addressing modes in the assembly language. But addressing in this context doesn't just mean memory. It also means how we deal with registers. The Z80 instruction set actually operates mostly on registers rather than directly addressing memory. So most addressing modes relate to how we handle the contents and arrangement of these registers. As we saw in the previous episode, the Z80 has a single 8-bit accumulator called A, and then 6 more general-purpose 8-bit registers that can be paired off into 16-bit registers. Then there are the alternate registers that can be swapped out with those, as well as a few 16-bit registers for the program counter, stack pointer, and index registers, which are all meant to store memory addresses and can be used to interact with memory in different ways. The simplest addressing mode in Z80 assembly language is the implied addressing mode, which means that the mnemonic only has an instruction abbreviation and no operands. That also means that the machine code for these instructions only consists of an opcode and no operand bytes, but the opcode itself may be 1 or 2 bytes long. These instructions may have an effect on registers and/or memory, but those registers and addresses don't need to be called out in the assembly code as operands. In some cases, there are instructions that have both implied modes and non-implied modes, and in the latter case it will have operands to specify a different way that the instruction can work, using different registers, memory addresses, or values. In the last episode, we saw how the load instruction works, and how it always has a pair of operands, with the destination of a value first, then the source of that value after the comma. Each of those operands has its own explicit addressing mode. We also saw these examples, where those modes dealt with either registers, memory addresses, or immediate values, but now we will get into each of those in detail. The most basic explicit addressing mode is the register mode, where we are simply dealing with the values in registers, which can be either 8-bit or 16-bit values, depending on which register is specified. The operand syntax is simply the name of the register, which is 1 to 3 letters long, as you can see here. Even the accumulator and status byte can be combined into a single 16-bit register called AF, and you can use the EX instruction to swap it out with the alternate AF, which in this case is formatted as AF prime, The one case a special character is used for register addressing. Register operands do not require any memory access on their own behalf, but they can be combined with operands in other modes that will access memory. In the machine code, the registers specified are encoded within the opcode, and not in extra bytes after the opcode. In fact, almost all of the load instructions between registers result in just a single byte of machine code, so the only memory access is to fetch that one instruction byte from memory, as specified by the program counter, so they are pretty fast. Immediate addressing means that the value you are referencing is right in the code itself, rather than somewhere else in memory referred to by its address. Instead, an 8-bit value is used as an operand, which in assembly language can be formatted as an integer in either decimal, binary, or hexadecimal. The range of an 8-bit integer is from 0 to 255 in decimal, which is 8 ones in binary or FF in hex. Effectively hard-coding this value is not quite as fast as just having that value maintained in a register, but it is quite a bit faster than having to fetch it from somewhere else in memory. Extended immediate addressing is just like regular immediate addressing, except that it is dealing with 16-bit values, also right in the code as part of the instruction. These values could be just regular integer values up to 65,535, or addresses that you are loading into a register. The immediate unconditional jump instruction is just JP with the target address after it, and all that happens in that instruction is the address in the operand is loaded into the program counter, rather than the address of the next instruction in the code. While extended immediate mode has a value as an operand, just plain extended or direct addressing has the address of the value in memory, rather than the value itself. This is signified by having the 16-bit address surrounded by parentheses, which means that a fetch will happen with that address, and depending on the operand order, this address will be read from or written to. This mode is only used with the load instruction, and only in conjunction with the register mode, which means that memory can only be read into a register and can only be written from a register. The width of the register determines the amount of data being transferred, with 8-bit registers loading a single byte and 16-bit registers loading 2 bytes starting from the specified address. There is no Z80 instruction to directly copy between memory addresses, or modify any memory value in place. In most cases, you are going to deal with memory addresses not directly in the instruction code, but in a register. We do this by using register indirect addressing. In this mode, the address in question needs to be loaded into a 16-bit register, either directly from a load instruction or as the result of a calculation. You can use BC or DE to load values to or from the accumulator, but in most cases you need to use the HL register. Any memory location can be used like most general-purpose registers if its address is currently in HL. To use the address in one of these registers for indirect addressing, you simply surround the register name with parentheses, just as you would for a direct address. Unlike direct addressing, there are no instructions that can load more than a single byte from the address. You are either loading a byte into an 8-bit register or doing some sort of operation on that single byte in memory. Locations in the first 256 bytes of memory can be referred to by 8-bit addresses, as the high byte or page number of that address is 0. This is why it's called the 0 page for architectures like the 6502, or page 0 in the case of the Z80. There are 8 specific addresses on page 0 that can be the start of a subroutine called using the RST instruction. These are technically known as reset vectors, but in the case of the ZX Spectrum, they are just special ROM routines that have dedicated shortcuts for calling them, and we'll see one of those routines in the example. We'll get into the other routines in later episodes, but just know for now that these addresses may be operands within the RST mnemonic. They are not actually in the machine code. Each of the 8 RST instructions have unique single-byte opcodes, so the address is implied by the opcode used, rather than having an arbitrary address in the machine code. This means that these 8 routines can be called with a single byte of machine code, rather than a 3-byte call instruction using the full 16-bit address, which takes 3 times as long to fetch during execution. Those 16-bit addresses can take up a lot of memory in your code, which of course also has a performance cost. But in some cases you can use relative addressing to jump to another part of the code if it is close enough that the value in the program counter only needs to change by an 8-bit offset. That means either subtracting up to 128 or adding up to 127, and then we can just use that offset in the instruction, saving a byte that would have taken up space in the program and get fetched repeatedly later. The assembler makes this easy by letting you just use a label to mark the location in code that you want to be able to jump to. If it's too far away, the assembly will fail and you won't be able to use relative addressing and have to replace it with extended immediate addressing. For most cases, this is as simple as changing a single letter of assembly code, replacing a JR instruction with a JP instruction, and keeping the label the same. A JR, or relative jump, will use the offset, while a JP, or absolute jump, will use the full 16-bit address of the label. If you think the jump destination is going to be close enough, it's good practice to use a JR when you can, and then only change it to JP if you have to. The DJNZ instruction is a special case where there is no absolute alternative, so you'd have to re-implement it with a separate decrement B followed by an absolute jump if not 0. We'll see how that works in a later episode, though. The index registers, IX and IY, have their own special addressing mode. It is like the register indirect mode, but instead of just using the address in HL, you can use the address in IX or IY with an 8-bit offset applied. So you can place IX or IY in parentheses, along with minus a value of up to 128 or plus a value up to 127. This is helpful when you are dealing with structured data, and you know the offset of different fields or instances relative to the address of your current instance, which you would load into the index register. Just be aware that index mode instructions will always be 2 bytes longer than corresponding HL indirect instructions because of a larger opcode and that offset, so be careful not to overuse them. Remember, every byte and cycle counts in 8-bit development. If addressing a whole byte isn't granular enough for you, there is bit addressing, where you can read, write, or test the value of a single bit. That bit can be either in a register or at a memory address stored in HL, or an offset from an address in an index register. The bit number is used as an operand, 7 for the most significant bit and 0 for the least. The bit instruction will test the bit, the set instruction will set that bit to 1, and the RES instruction will reset the bit, which means setting it to 0. This becomes especially important when dealing with hardware interfaces, as we will see in a later episode. So that's all the supported addressing modes according to Zilog. But wait, there's more! More modes really than are acknowledged officially. So since they don't have official names, I've come up with my own names for them. Assembly operands can also be status conditions, representing the state of particular bits in the processor status byte. These conditions have similar names to registers, also consisting of 1 or 2 letters, and their identification as conditions rather than registers is based on the instruction being used. Conditions are only used for instructions that result in the program counter jumping to another location in code if those conditions are currently true. We'll get into what these conditions mean in a later video, but the most commonly used are the carry or C bit and the 0 or Z bit. Of course, there's a C register also, but when we see a C as the first argument of a jump instruction, we know it's referring to the carry bit, and taking that jump only if the carry bit is currently set. If the operand is NC, then the jump is taken if the carry bit is currently clear. It's through these conditions that the Z80 becomes truly a Turing-complete CPU, allowing us to do conditional branching and looping. Oddly enough, the interrupt mode is not an official addressing mode, but it is certainly used that way for the IM instruction, which stands for, of course, interrupt mode. The Z80 has 3 different interrupt modes, and there are 3 different IM opcodes to tell the Z80 to enter them. The assembly instruction just has a 0, 1, or 2 after IM, But that number is not in the machine code, instead being encoded into a 2-byte opcode, with neither of the bytes being the actual number of the interrupt mode. For the Spectrum, interrupt mode 0 is not used at all, so we'll never actually use that particular instruction. We will use interrupt mode 1 when using the interrupt handler built into ROM, but more often we will use interrupt mode 2, where we can define our own interrupt handler, which we'll see in a future episode. Now that we've seen all the different addressing modes, it's time to use all of them in a single example program. At the end, we'll have a needlessly complicated program that will generate a little bit of text on the screen. Let's dive in. We're going to be using Atom again, which you will see has the ability to do some nice syntax highlighting for all of these addressing modes. Just like in the last episode, we start with a device macro specifying the 48K spectrum, and then an org directive to start our code at hex 8000. Our first instruction is a jump to the start label, using the extended immediate mode so that we can have all of our data defined right at the top of the code file. We don't actually have more than 127 bytes of data, so this could have been a JR instruction and saved a byte of memory, but we'll stick with JP so that if we did want to add more data, and in most applications you would, we won't have to change this instruction and just use it as the last part of a standard header. After the jump start, we have our data, which is just a 5-character string reading hello in all lowercase letters. Before the data, we have a label named string that we can use to retrieve it later. We use the DB directive after the label, as that means data byte, and we can have a set of comma-separated numbers or strings quoted after it, or even a combination of both. Strings will be in the character set of the source code, which in this case is ASCII-compatible UTF-8. Luckily, this matches up with the standard character set of the Spectrum, at least as far as letters go. Then we have some constants, which don't take up any space in our code, but just act as identifiers that we can use for numerical operands without having to hardcode the actual numbers in our instructions. First, we want the length of our string, which is 5. Then we have some addresses we need, starting with the clear screen routine in ROM. That has the address hex 0DAF, and that will be the case with the ROM for any variant of the Spectrum. Now we can just call romcls, and that ROM routine will be executed, and then return back to our code with the entire display cleared out with the current paper color, and we won't have to have that address anywhere else in our code. Then we have another address, this time in the screen memory, with color ATTR set to the beginning of the color attribute data, which will be used to set the paper and ink colors for every character position in the display. With all of the relevant addresses defined, we move on to some other values we'll need in our code. First, the Spectrum character code for the enter key, which will make text start printing at the beginning of the next line after you print it out with this hex 0D code. Note that this is different from the usual hex 0A code for an ASCII line feed on most systems. Finally, we have a constant that we can use for color attribute memory, which will specify white ink on black paper, which we'll call black-white, as the paper color comes first in the byte, as we saw in the last episode. Then we finally get to the proper beginning of our code at the start label. Our first instruction there is IM1, meaning that we are setting interrupt mode to 1, which will bypass any custom interrupt handler that may have been defined previously and just stick with the handler in ROM. This is the best approach for this program, as we will be depending on the ROM code to properly render characters when we print them, and we have nothing special that we need to do in response to an interrupt. Then we call romcls using the extended immediate mode again, as we need the full 16-bit address for all call instructions. A call, unlike a jump, will expect the routine it calls to end with a return instruction, so that the program counter will return to the next instruction afterwards. So once the screen is clear, the ROM code should return to the following load instruction, which loads the address of our string data into HL. So the first operand of the instruction is using register addressing by just having HL with no parentheses, then extended immediate by having the string label also without parentheses. If the string label did have parentheses around it, that would be regular extended or direct addressing, which would load the first 2 bytes at that address, namely the lowercase h and e character codes, and store them into the HL register. That would have meant H in the L register, ironically, and E in the H register. But by omitting the parentheses, we get the address that the assembler calculates for the string label, which should be hex 8003, as it should be right after the 3-byte jump instruction that we know started at hex 8000. This means that the high byte of the address will go into H, which is hex 80, and the low byte of the address will go in L, which is hex 03. Now you can probably guess how H and L got their names. Then we load string length into the B register using the immediate mode. We're going to use B as our loop index, which is a common pattern for Z80 programs. Then we go into our loop with the beginning labeled loop, so we know each iteration will start right here. The first thing we do each iteration is load a character from the string into A. We do this with register indirect addressing, putting HL in parentheses so that the address in there will be fetched to get the value that will be loaded into A. Then we do an RST to hex 10, using that modified page 0 addressing. This calls a ROM routine that prints the character code in the accumulator to the screen. So this should result in printing the character we just loaded from string at the address in HL. Then we increment HL, which will make the address there point to the next character. Then we decrement B, noticing that we have now done unary math operations on 2 registers in a row. First a 16-bit register and now an 8-bit one. 16-bit increments do take longer, as they may require doing a carry to the higher byte. After B is decremented, we check to see if it is 0 yet, and if it's not, we jump back to the top of the loop. We do this with a conditional JR, using the NZ condition for non-zero, and the relative offset to the loop label. If you are an experienced Z80 programmer, or are paying close attention earlier, these last 2 instructions could be combined into a single DJNZ instruction, using just the loop label. But then we would have missed out on seeing all of these different modes. Also, we may have to end up using B for something else later, so it may be a good idea to break it out like this so we can change the register used later. Once B gets down to 0, we have printed out all 5 characters, and we stop looping and instead continue on to the instruction where we load the enter character code into A. We print that out, and now our invisible cursor has moved to the beginning of the second line. To change the color of that initial H we printed out, we load the accumulator with the black-white color attribute constant we defined earlier. We then write that to the first byte of color attribute screen memory by using direct addressing with the color attr constant we defined earlier, and loading the new color attributes in A to there, which will make the H white on a black background just in the little 8x8 pixel square surrounding it. Now we're going to print out that string again, but this time a bit differently by using the rest of the modes at our disposal. First, we load the string address into the IX register, which will look exactly like the earlier instruction where we loaded it to HL, but the machine code will be preceded by a special byte saying to use IX instead of HL, so this will make it take a bit longer to execute by adding the extra byte to fetch in the code. Before we start printing the characters, we modify the first one by clearing bit 5 in the character code. This will change it from hex 68 to hex 48, which effectively capitalizes it. We do this with the RES instruction, with 5 for the bit addressing, and then IX in parentheses to use indexed addressing for the location of the byte to change. This is not register indirect addressing like we saw when we had HL in parentheses, but indexed because what we have is an index offset of 0. We could put +0 after IX in the parentheses to be more explicit, but it's not necessary in the assembly code. It is necessary, however, in the machine code, and we will have that 0 byte after the opcode. In this case, the opcode will actually be 3 bytes long, which is as long as opcodes get, and we still have to have that 0 to pad it out to 4 whole bytes. If we had used HL instead, this instruction would have been a trim 2-byte opcode with no additional bytes afterwards. Now you can see the real cost of using indexed mode, especially when you don't have to do any actual indexing. But for the sake of this lesson, we will do some actual indexing, which we will use to unroll the loop. For each character, we load its code using its string index as the offset from IX, starting again with an implied 0 for the first character, followed by another RST10 to print it out. Then we do IX plus 1, plus 2, plus 3, and finally plus 4 to get all 5 characters in this unrolled loop and print them all out on the second line of the display. And then one more enter code to get past the second line. And that's all we need to do. So we'll just do a final return instruction, which is the only implied mode instructions we have used here. And that's the last one we needed to do. We have drastically overcomplicated printing out 2 strings using every last addressing mode available for the Z80. All that's left in this file is to create a deployable artifact, and we'll just go with a snapshot again. In later episodes, we'll be making tape images too, but we've done enough for this example already. What we will do this time, however, is have a build script, which we have right here in another tab. Here's build.sh, which is a Unix-style shell script. So we have the business at the top where we indicate the program needed to execute it. On any Unix-like system, /bin/sh is the most basic shell program, and pretty much any standard shell, including C shell and bash, can run sh scripts. We only need one line, which is to call sjasm+, assuming it's on the path, and then the -lst option to generate a machine code listing, and finally modes.asm, which is the file name of the assembly code file we just went through. This will generate 2 artifacts, the modes.sna snapshot file we specified in the savesna macro, and modes.lst, which will have the machine code listing generated as a result of using that option, which doesn't require a file name on the command line. It will simply take the name of the assembly source file and change the extension to .lst, and we'll be able to see how each instruction was translated to machine code in a human-readable text file. So let's go to the terminal and run this script right now. We simply run build.sh, and then we do a directory listing, and we can see both of the artifacts that we expected, modes.sna and modes.lst. Let's go back to Atom and take a look at the listing. Here we see all of modes.asm, but this time with 24 characters added at the beginning of each line. First, there's the line number from the original file, then the hex address of that line. As we can see, it starts out at 0 until we get to the org statement, where it jumps to 8000 for the next line. The jump start instruction starts at 8000, and we see the 3 bytes of machine code generated for that, all in hex. C3 is the opcode for unconditional jumps using extended immediate addressing. This lets the Z80 know that 2 more bytes are coming, and they are going to be an address to load into the program counter. So we see that address as little endian, with 08 followed by 80, which means that the start label has been resolved to address 8008, which we can see below. We see the 5 character codes in our string, which requires a second line, but you can see that the line number 8 is used for that second line still. You can see that the constants do not affect the address as no data is being stored, and we ride address 8008 all the way down to start. Then we have that IM1 instruction, which gives us the 2-byte opcode ED56. When the first byte of an instruction is ED, we know that this is going to be a 2-byte opcode, so the Z80 will fetch another byte to see which instruction this is. 56 indicates IM1, which doesn't require any machine code operands, so we'll go right into that mode. If the second byte was 5E, that would have meant interrupt mode 2. That doesn't make a ton of sense, but that's just how the Z80 opcodes are set up, and we'll get into that more in later episodes. Then we see the machine code for call romcls, which starts with CD, which is the opcode for an unconditional call using extended immediate addressing. That will be followed by a little endian address, which we can see is AF0D, which is flipped around from the constant we defined as 0DAF. An important thing to remember is that 16-bit values need to be big endian in the assembly code so that they will be properly translated to little endian in the machine code. This makes sense, as big endian is friendlier for humans, But little endian works better for the little transistors in the Z80. Then we have the LDHL string instruction, which gets us 21 for an opcode, which means load HL using extended immediate addressing. So 2 more bytes are expected. As this will be a little endian 16-bit value, the first byte will be the low one, so the Z80 will put that in L, and then put the second one in H, as that will be the high byte. And we can see here that will be 03 followed by 80, because the string label resolves to 8003, as we saw earlier. After that is LDB string length, which gives us 06 for the opcode, which means load B with immediate addressing. You can see that we already have 2 LD instructions with entirely different opcodes. There are many, many opcodes for LD, each referring to different combinations of sources and destinations, with some of those opcodes being 2 or 3 bytes, and then requiring between 0 and 2 more bytes for any non-register operands. It can be quite confusing, but luckily the assembler can keep it all straight for us, and will let us know if we try to use any invalid addressing mode combinations in our operands. I won't go through any more of this, as you can run this build yourself and look through the listing at your own pace. It should provide a lot of insight into how these different addressing modes work in both the assembly code and the machine code, and how they relate. But we will go ahead and scroll down to the bottom anyway, and see that our whole program only takes up hex 40 bytes, which is only decimal 64. Pretty short program, but it will do for our purposes. Let's finally get it loaded up in the emulator. Again, we're using Zesarix, so we hit F5 to bring up the menu, and then select Smart Load right at the top. Then we select modes.sna, and that will run it. Now we can see exactly what we expected. The first line has hello with a lowercase h, which has been modified to use white on black color attributes, while the rest of the text uses the default black on gray. On the second line, the H is capitalized, and that's it. Our emulator is kind of in limbo because that return at the end had nowhere to return to, because no basic loader was used. But we'll see how that works next time when we start going into these instructions in detail. As for this episode, we're done. Please subscribe to my channel and click the bell to be notified when the next episode comes out, and please like this video if you learned anything, and let YouTube know that you want to see more tutorials like this. If you can't wait for the next episode to go public, join our Patreon community and see my videos ad-free as soon as they are uploaded, just like the people you see here. Thanks for watching, and I hope to see you again soon. Bye-bye.